quickly to get started, we have a few terms here. Programming and coding kind of go together and pretty much mean the same thing. There's just a small distinction that can kind of be useful to know about. Basically, programming is conceptual, whereas coding is literal. Both of these deal with algorithms, but programming is sort of just ideating, whereas coding is taking those ideas and turning them into actual executable, like, computer tasks. And then I've probably described this to you before, but an algorithm is just a series of finite instructions, basically. Things that make algorithms actually useful. We have conditional statements, anything involving an if this, do this, else do that. We have looping, which can be like, while this conditional is true, continue to do this. Then we have things like functions, which, given this input, return this output. These are just tools in our toolbox that make computing useful. So when we program, technically speaking, this is like language agnostic, and coding is like kind of what we're going to learn to do. Specifically take a C++, in our case, a programming language, and write literal code that performs a series of algorithms to accomplish tasks. So something that I think will be interesting to do along this course is to integrate like the use of language models to kind of show a bunch of stuff. So to get started, I wanted to use ChatGPT, and you can select your model here. This doesn't matter a ton for our use case because we're mostly doing simple stuff, but I'm going to use ChatGPT to show us kind of a rough feel for C++ versus Python, which kind of represent two different paradigms in programming, and I will go over that right after just giving you the literal example here. Okay, so here's what we're asking ChatGPT. Show me a beginner-friendly example of Python code versus C++ code, and our goal is just to kind of see the basic syntactical differences. This is not the most useful example, so it doesn't really matter a ton. Here's a decent example to go over. We have Python versus C++ running a simple for loop. So we're basically just printing the numbers 1 through 5. And so for Python, you can see we accomplish this in 5 lines of code, whereas in C++ it takes a lot more. This is just stuff that we're taking note of. We don't necessarily need to know the reason yet. We'll go over why, and that will be an interesting point of discussion. Let's go over one more example here. We have, looks like an algorithm to compute an average, which is just the total sum of some items over the number of that array of items. And then it looks like this is running something to add numbers to a list and then compute that average. This is going to look like hieroglyphs to you, potentially, but don't worry about that. We don't need to know everything here. We're just looking for general syntax. So here we can see we're defining a function. Here we're doing an if statement. Here's another function. And in C++, same thing. Here we're defining a function. Here we're doing an if statement. Just notice the slight differences between the two. It's kind of what we're going for. There's this weird syntax for C++ that we're seeing occasionally. Here's a while loop. Up here we also have a while loop, but you'll notice they're a little different in syntax. Okay, so this is a quick diagram to kind of explain what's going on here. There's sort of an inverse relationship between human readability, which is the same thing as something that's high level, versus like what the computer sees literally, which is considered low level. So high and low level languages basically are just describing like how similar to the bare metal are you getting when you're writing your code. An interesting process that occurs with any code that you write is something called compiling. You've heard me talk about this before. Basically, compiling is taking your code and turning it into a series of instructions that the computer can actually understand. So when you write, for example, x equals 5, what you're really doing is taking that code, turning it into something called assembly code, and then that assembly code is turned into direct binary that the computer processes and uses to alter its hardware. So I'll quickly show you an image of what that looks like. So here I've asked ChatGPT to show me what assembly code and then the binary looks like for what compiles in C++. When you first set a variable y, and then you set x to be equal to y plus 5. So you can see here, this is the C++ function, this is the assembly, and then this is the binary itself. We have an integer function. Foo is just a common programming term for like meaningless. In our function, we receive an integer y, we declare an integer x and set that equal to y plus 5, and then we return x as the result of our function. Try to interpret this now. Not so easy. And then this, impossible. So the entire purpose of programming languages is to help humans be able to develop things in a way that we can actually understand. As we get higher and higher up this graph, we get more and more into languages which have opted for human readability as the primary value. So what's the trade-off? Why would anyone ever want to use C++? Well, it turns out the more human readable you get, the more work the computer has to do under the hood to interpret the commands you're giving it. In some sense, you are giving up control over the hardware by using one of these more human-friendly programming languages. Just to quickly explain a little more about what I mean here. Notice for C++, when we declare I, we tag it with this int first, and same with our function. We tag it with this int. What this means is we're saying this value should be an integer, and when the computer sees this, or when the compiler turns it into something the computer sees, what it's literally doing is saying allocate a certain amount of memory to this value. Whereas in Python, you don't get that at all. I is just sort of interpreted for you as an integer based on its use case. A lot of the work in terms of like actual allocation of memory is done under the hood, kind of abstracted away from you, and that can be really awesome, but it depends on your use case. And our use case is to learn what's actually going on with a computer. And so it kind of helps to use a language that lets us talk more like a computer would see. And so for us, being able to do these literal type declarations at all times is going to be a very useful thing to see sort of the underlying process going on with a computer. If this doesn't make a ton of sense, don't worry. Generally speaking, just know that Python is a language that abstracts away a lot of computer nuance, whereas C++ leaves it up to you a bit more. And this will definitely make a lot more sense as we continue to use C++. Just in case it wasn't clear, Python also has a compilation process. So this would be going to assembly code as well, and then it follows the same chain from there, where this assembly code is turned into binary. So an interesting thing here, you'll notice that in the course, which was written in 2011, it says that C++ is a high-level language. This is a perfect example of how quickly things in the programming industry change. Because as you can see now, these days C++ is actually considered pretty low level. At the time of writing, this was considered a high level language. Next we'll get into C++ specific like syntax and details with the language. You'll notice here he goes over a hello world code. There's nuance here that makes this kind of bad for a first example. So we're going to come back to this. So here he has a pretty comprehensive list of different tokens that exist in C++, and a token is just like a word, basically. And different words have different meanings, as you might expect. So we've already encountered int, we've already encountered for, but there's tons of these tokens, which are, he calls keywords, and these represent different instructions that your computer will see and execute based off of. So if I declare an integer and I name it x, and then I do x plus 5, the computer is going to know how to manage x because we declared it as an integer. So we have keywords, which are things that are special to the C++ language. Then we have identifiers. This is a fancy name for the thing that we name our variable. So you'll see x, you'll see my function. This is like for us to decide. Then we have literals. What these mean is just like the values of stuff themselves. Just think of this as variable and think of this as value. And we have operators. I wouldn't overwhelm yourself with like what all these mean yet. Leave it to when we actually establish context for how to use them to learn them. But yeah, these kind of compose your programming language. So we'll use these and understand these pretty familiarly as we go on here. He gets into some more nuanced C++ stuff here. I don't think it's super relevant for us just yet, but we'll probably run into this stuff later, and I think it'll be a lot more effective to learn them as we see them. He makes the distinction between a statement and an expression. An expression is just like some way of representing a value, whereas a statement is something you're telling the computer to do. Operators are what let you manipulate values, and so like these are kind of the core of programming. You have mathematical ones like plus, minus, times, divide. He goes over another one called the modulus operator, which we might see at some point but don't need to know yet. There's logical stuff, and or. Looks like we cover these in the next lecture, so I won't get into it too much, but if you've ever seen me write code with a double ampersand or these two lines, these are logical operators. So we could say is enabled, for example. We could say is enabled and is ready. Both of these together might be used to perform some action. Kind of a random example, but another way you could write logic is with an or statement. And so what this means is if either of these is true, then maybe we perform some action. So double lines like this is or, double and like this is and. And this is pretty common across many programming languages. So before, when I mentioned integers, I was saying the computer sees this and knows to allocate a certain amount of memory to represent this number. You'll see an integer is just a 4-byte data type. And what that means, a byte is 8 binary values. And so if we have 4 bytes, an integer represents this much space in our computer. Let's say we have int x equals 0, right? Basically saying x is equal to this. If we say x equals 1, what does that look like? Boom. X equals 2. Because we're in binary, we can't do this. That doesn't exist. Instead, we have to write this, because all these values can either only be 0 or 1. And so we choose to represent this number by this arrangement of values. So an integer gives us all of this to work with. A double would be twice the size. It mentions two other ones here that are pretty nifty. A Boolean can either be true or false. Weirdly, you'll notice this takes up a full byte, where a byte is 8 zeros, but it's only ever equal to true or false. And so what this means is we're only ever using this last bit, but that's just because it's convenient for the computer to work in bytes. The types of operations that are relevant for the data type you're using is something to note here. If we're using a Boolean, it makes no sense to add or subtract. And in fact, if we do, our compiler will tell us there's an error. If I were to write is enabled equals is enabled plus 5, this will not compile. Weirdly, I think this might compile. We'll have to look at it. It's been a while since I've looked at C++. If this does compile, which I have a hunch it does, it's doing something weird. Turn it into what's 5 letters next in the alphabet? It's going to be either E or F or something like that. But this is probably not good behavior, so ill-advised. Here he goes over variables, so he declares an integer x. We've already seen this with our brilliant examples over here. And then he says x is equal to 4 plus 2. So he's actually broken this into 2 lines. You'll notice I wrote shorthand here, saying int x equals 8. This is actually 2 computer instructions in one, and it's just a nice, like, C++ syntax that you're allowed to do. Here he's saying integer x. He's just declaring the value which tells the computer, allocate memory for this, and I'll deal with it later. And then in the next line he says, okay, take that memory we've allocated and assign it this value. Like before, I'll write out the memory registers here. What he's doing is he's saying declare x and have it take up this memory. And then in the next line he's saying x equals 4 plus 2. Take this binary value of 4, add it to this value, which is this 6 value. X is going to now equal this value in memory, right? I'm getting really deep into the weeds here, just so you have an idea of what operations are going on under the hood. Like, this is directly managing system hardware. We take this C++ instruction and turn it into a computer instruction. Okay, he talks a little more about this like input and output thing. We're going to see this when we actually write code, so I'm not going to go over it yet. If you're curious, you can ask a language model or look up what these are. Okay, and then lastly, he talks about this idea of debugging. And I think this is actually a pretty interesting point. He talks about the difference between compilation errors and runtime errors. So a compilation error is a lot easier to deal with usually because it's something that the computer will yell at you for before you even execute your code. So if we set isEnabled to false and then we say isEnabled equals itself plus 5, the computer literally cannot compile this. There's lots of different types of compilation errors. C++ is pretty strict with its syntax. We actually already have a compilation error here too, and it's because we didn't end our statement with a semicolon. So if you would just write int x and then move on, this is actually a compilation error as well. We need to write our code in a very specific way for C++ to know how to take it and turn it into computer instructions. Quick note about this annoying semicolon thing. Other languages have done away with that and often represent a new line or pressing enter as the end of a statement. So in Python, what you'll see a lot is like, if we have some value x equals 5, we can just move to the next line and then say x equals x plus 10. Python does some stuff that's even cooler with its structuring where you have tabs represent scope. So inside this tab, we know we're inside this function that we've defined. So here we're saying define add1, which is a function that takes a value x, and it returns x plus 1. And so here, we've defined our function, and because we've tabbed in here, this is within our function. And then when we tab back out, we know we're dealing with stuff outside of the function. Now with this, because we pass in x where x is 5, x is going to be equal to 6 at the end of this. So different languages have different ways of structuring things and different rules behind what's allowed to be compiled and what's not. C++ is pretty strict. It's closer to what you're seeing the computer actually doing. Okay, so then what's a runtime error? If that's a compilation error, what's a runtime error? These are a bit trickier, and they usually represent things like bad memory allocation or bad memory accessing. This is getting a bit advanced, but let's say we have an array, and the array is of size 5. This is how you know I'm out of touch. I have to look up how to declare an integer array. And so what you can see here is we have an array of size 5. That's what this bracket notation is. Again, this is just syntax. We don't need to memorize this yet. And then we declare our array as a comma-separated list enclosed in these curly braces. And this is just C++ syntax. The more we use this, the more sense it'll make. But anyways, so we can access these values with the same bracket notation. We're saying grab the value at index 0, which is, in our case, 0. If this were 5, then this value would be 5. So we could say something like int x equals array at index 0. And this means x is equal to 5. So if we did x equals x plus array at index 1, now x is going to be equal to 5 plus 1, or 6. If we did 2 here, we would have 7, and so on. But what if we did something fucked up? What if we said x equals the value at array of index 6? Well, this is clearly outside of our defined array here. We've tried to access memory that we're not authorized to access. I think the formal name for this is out of bounds error or something along these lines. But you might be wondering, don't we know that we declared an array of size 5 here? And shouldn't we know then that accessing the index 6 is impossible? It turns out the way that arrays are written under the hood follow a more nuanced structure. At compile time, we don't necessarily know by the point we're reaching here that the index 6 is outside of bounds. To quickly illustrate this, if we have an array of size 5, it might look something like this: 2, 3, 4, and 5. What the computer under the hood is going to do is create this thing called a pointer. So our magical array value is going to point here. This pointer is at index 0. So all we've done by declaring this integer array variable is created this pointer guy. This pointer doesn't know the size of our array. We've allocated this memory somewhere else. This pointer just points to values, and we can say point to value 0. We can also say point to value 0, 1, 2, 3, or 4, and then we could also say point to 5. And if we try pointing to 5 here, we're breaking things. So if this doesn't make sense, that's okay. Just know that under the hood, things look a bit different than you might expect. So that's just one example of a runtime error. There are other examples too. Another common one is called a stack overflow. And a stack overflow is basically if your computer allows you to allocate a certain amount of memory to a program. Let's say we declare an integer array of size 9999999999999. That's a lot of integers to allocate to a single program. And this very well could be outside of the limit of what your computer allows you to allocate for the program at hand. If that's the case, you have what's called a stack overflow. We'll get into why it's called this later, but just another example for you.